Hello and welcome back to another video with It's Dr. Dan, and today we're going to be learning about oxidation reduction reactions. Now, what makes oxidation so excited is that it's something that is around our entire world. It's what allows us to function. It's what allows the entire world to work. Well, we can see it around us. If you go outside, right, you see that the different plants that are around you are going through photosynthesis. This is a process of oxidation. You right now are functioning via oxidation reduction. Your digestive system, the cellular respiration that's occurring inside of you, your metabolism, all of these are all working through oxidation reduction. Now, when it comes to other reactions that are occurring as well that you see around you, you being able to watch me right now, it's probably thanks to oxidation reduction, especially if you're on a laptop, a cell phone, a tablet. All these different devices are powered via batteries, which are constantly all about this process. Now, what is it? Well, oxidation reduction is also commonly known as a redox reaction. And all it is how electrons are going to be moving in between atoms. So when we are trying to look at this, we are going to be seeing how electrons can be transferred from one species to the other. And this is going to be the entire idea here. So when we're looking at this, well, we can explain it through some simple ideas. Is that oxidation is all about the loss of an electron. Reduction is all about the gain of electron, which can sound a little confusing when you think about reduction. It's like, how is it gaining when it sounds like reduce? So we'll talk about that here in a second. But let's just go back to just trying to label our little atoms here and how exactly can we label each of these species? Well, which one of these, within every oxidation reduction reaction, there are always a pair, meaning that if one species is being oxidized, the other one must be reduced. So, being that we have on the left here, we have A is giving away an electron, it's being donated to another species, or aka it's losing its electron. You can see on the left, we have that it is being oxidized. And now on the right hand side, well, being that you see that B is receiving that electron, this is being reduced. So this is all we are trying to see in this video, and through trying to understand this is where can you see the hidden chemistry occurring within a reaction? Sometimes you might only see it looks like a normal single displacement reaction, a normal combustion reaction, but there's something hidden behind the scenes, hidden within the charges or the oxidation numbers of these different species. And that's what we're going to be seeing today. We're going to be learning exactly what this means and how it is that we can understand the different phrases that we're going to see. Let's take a look at a little bit of all of this together. Now, trying to keep oxidation reduction straight can be extremely tough. Well, how do you know which is which? Well, oxidation, loss of electron, reduction, gain of electron, that doesn't really quite make sense. Well, the first thing is trying to understand reduction, right? It's gaining an electron. Well, where does the word reduce come from? Well, the way that we got to look at that, it's all about how we are reducing the charge, right? Whenever you are gaining an electron, you got to remember that the number is going down, 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 down. It's becoming more negative because electrons are, the more you add, the more negative it becomes, which is the idea here, right? It's all about trying to change it. So what it all comes down to is trying to remember little cute mnemonics for you to never forget oxidation reduction, because this is a phrase that you will need for chemistry, for biology, for physiology, for biochemistry, for all these other courses in it, because it's so important. So remember the phrase Leo goes GER, which you will never forget what it means for oxidation reduction. So Leo the lion, loss of electron is oxidation. Okay, loss of electrons is oxidation. So where does the Leo part come from? Well, if I just kind of underline that for us, we got loss. The loss of electrons is oxidation, and that's where that is coming from. Now, the other one, which is reduction, is gain of electrons. Gain electron is reduction. So loss electron, oxidation, gain of electron is reduction. So Leo goes GER is the way that we are going to remember this. So all you got to do is remember how a line is growling at you or GERing, and you'll never forget that little phrase to help you be able to label these. And that's what we're going to do through this actual chemical reaction. Let's take a look. All right, so in our first example, what we're going to be doing is labeling oxidation states. So what an oxidation state is a way for us to essentially do some electron bookkeeping to determine where are the electrons moving within the reaction. They do not always represent the actual charges, but they do tell us what kind of chemistry is occurring. So the first thing is being able to tell the difference between ionic compounds and atomically neutral elements and compounds and these different molecules that we'll see. So first is as I have sodium and chlorine and they are combining together to make NaCl. So what I have here is I have two different species over here. These are different atomic species that, if you remember from your periodic table, are inherently neutral. Okay. So being that these are neutral, what oxidation state could we give them? Well, they're both going to have an oxidation state of 0. So when you have a pure substance or a diatomic gas that exists in its natural state, they have what we refer to as an oxidation state of 0. Now, the only difference between oxidation state and ionic charge is that ionic charge is the actual charge of losing and gaining electrons. This is very similar, but we use different terminology to describe it. So on the right-hand side, I have an ionic compound, meaning that there are charges, which we can use the charges to tell us what are the actual oxidation states. So if you remember, sodium has a +1 charge, chlorine has a -1 charge. So what this can help us see is, well, what species is being oxidized, which one is being reduced. So the way that we can look at this is by observing something and looking at what we call a half reaction. What a half reaction it does is you write down the species from the left and the right side. So I have sodium on the left and it has a charge of 0, and it's going to be turning in to sodium on the right hand side, where it's going to be changing its charge to a +1. So it's going from Na0 to plus. Now the question is this gaining an electron or is it losing? Is it Leo goes GER? Well, being that our charge is, in this case, it's becoming more positive, so we are losing an electron in the process. So what we can see is here is that, oh, okay, well, sodium is being oxidized. Therefore, meaning that chlorine, on the other hand, must be reduced. Remember, they're a pair, so they each have to do their own unique thing. Now, how can we show that? Well, if I write down the charges for chlorine, it's going from a 0 to a -1 charge, meaning it's gaining an electron. The charge is being reduced and becoming more and more negative, and we're gaining an electron as a result. So, is this the only thing I can show in this half reaction? Well, we can illustrate that the electron is being gained as well. One thing you may have noticed is that I was writing down the symbol E with a minus next to it. That's referring to that we have an electron that's being gained. So what I can do is write E minus plus chlorine 0. And what we're trying to do is balance the charges on the two sides of the reaction. Notice how on the left side, I have a total of -1. And on the right side, I also have a total of -1. Now, this one on the bottom shows reduction. On the top, oxidation should be the opposite, showing the loss of an electron essentially sent away. So how we can show that is, well, if I have a 0 charge on the left-hand side of this half reaction up top, I should also have a 0 up here. So it's +1 plus -1, which mean I have to put my electron on the right. Okay. So this is one of the ideas, what we try to show with oxidation reduction, how the electrons are being transferred. When we have essentially a sodium, it's giving away, in this case, it's going to be giving away its electron to a chlorine. So it's being transferred from one to the other. So we can show how that electron will be transferred, which makes sense if you think about it, right? Sodium naturally has a +1 charge. So it's going to try to give its electron to chlorine so it can bond and react. So Leo goes GER. Let's look at some other examples to keep further our understanding here. Before we go into our examples, the first thing I should do is establish these little rules for you to be able to label your oxidation states. Now, for right now, this is an introduction to redox reactions. So we're just going to look at a very simple set of rules to get us through the basics for now. So the first thing is whenever you have a pure element or a natural state of an element, like a diatomic or sulfur, which exists as S8, or phosphorus, which has P4, these are always have a charge of 0. Or even if you have like a metal that's by itself, meaning it's not ionic, it's not bound to something, it's just alone. So whenever that happens, it has a charge of 0. Now, the other species are, well, if you have a cation or an anion within an ionic compound, their charge will equal your oxidation state. They will be the same number, which is good, right? It's like, oh, it's one thing that we really need for ourselves, make it easier. The other thing that's important is being that if you remember, ionic compounds are overall neutral. It applies the same here with oxidation states. The sum of the positives and negative have to cancel, meaning it has to equal 0, which is extremely important to see in these problems. Let's take a look. So in our first example here, what we are going to be looking at is assigning the oxidation states based on the simple rules that we said before. And keep in mind, we're just going to do a simple introduction of labeling oxidation reduction. So we're not going to be doing complete redox reactions. So the first part is that we have iron, which is in its natural state, meaning that it's going to have a charge of 0 next to the molecule or next to the atom. And that's going to be combining with 2 chlorine atoms, or the diatomic, which means it's also in its natural state. And we're going to assign that as a 0. Now, on our ionic compound, we are going to use our reverse swap drop to be able to see this. Well, if you remember, chlorine always has a charge of -1, meaning that if there's 3 of them total, so the total negative is 3 minus, so what does the overall charge of iron have to be? Well, to balance that out, it must be a charge of 3 plus. So we are going to put that charge right next to it, 3 plus, to help illustrate that we have our oxidation state as 3 plus and 1 minus for chlorine and iron. So now what we can do is we can label what our half reactions are, label what's being oxidized, what's being reduced here. So on our first one, we have iron is turning into iron 3 plus. So is this going to be gaining or losing electrons in the process? Well, we have that there are 3 less electrons on the right, meaning it's going to be losing 3 electrons. So if we are losing 3 electrons, what are we doing? Well, if you remember, Leo goes GER. So we are going to be oxidized in this case. Iron is oxidized, which just means it's rusting. Now, on our other one, we have chlorine. We have Cl2 is going to be falling apart into 2 chlorine ions, and that has a 0 charge and a minus charge. Well, how can we go through and balance this one out? Well, this one's a little bit different, is being I had to add a coefficient here to balance out the charge because we had, or balance out the atoms, being that we have a 2 on the left. We will have a total of 2 electrons that have to be gained to balance out the overall 2 charge on the right. So we have our oxidation reduction process. We're gaining electrons on the bottom and losing electrons on the top. That's one of the ideas when we're writing our half reactions. Now, let's look at trying to just practice assigning oxidation states. So when you're practicing these, sometimes you might have to fill in a table just like the one here, which is all about, can you just quickly assign these because you want it to be second nature to you. So the first one is P4. Now this one I picked because it's a little bit of a strange one. It is actually the natural state of phosphorus. There's some other weird ones you might see as well, which are like S8, for example, are the natural state. So other than the diatomics, these are some other ones. When they are in their natural state, so let's say if I have phosphorus 4, they're going to have a charge of 0 for all the phosphoruses that are available. Same thing with sulfur when it's in S8. They are going to have a charge of 0. Now on the next one, we have K2O, so potassium oxide. So how would we end up assigning that? So let's write down our species. Well, being that this is an ionic compound, right, a metal and a nonmetal, we will assign our charges like normal for our oxidation states. So we have 2 minus and then 1 plus for our oxidation states. So they are going to be the same as the ionic charge. Same thing with barium chloride on the next one. We have barium and then we have chlorine. Well, chlorine always has an ionic charge of -1. So that means it's going to have a oxidation state of 1 minus. Same with barium as well. It has a +2 charge for ionic charges, meaning it's going to be a 2 plus charge for the oxidation number. Now for iron, well, iron is right now in its natural state. It's referring to just the metal by itself. So what's the charge going to be? It's going to be 0. Versus the one that's below it, we have iron 2 plus. So its charge is also going to be, or its oxidation state is also going to be 2 plus. It's going to be the same general idea when we are looking at these different molecules and trying to see, okay, how is the oxidation state and the charges? How are they going to line up? The last one is O2. Well, O2 is the natural state of it, right? It's what you're breathing right now. So O2 is going to have a charge 0. So this is how we can practice it, right? It's the same as your charges. The only difference is that they're called oxidation states, and it's more for how are the electrons moving. Let's look at one last example. So practicing as quick as we can we identify what's being oxidized, what's being reduced? Let's label our charges. So with K2O on the left, your oxidation state for potassium is +1. Your oxidation state for oxygen is 2 minus. Now on the right-hand side, being that we have 4 potassiums that are by themselves, this is going to be a natural element that's all alone. It's going to have a 0 charge. Same thing with your diatomic oxygen. It's going to have have a 0 charge because it is by itself. So when we're trying to label these, we have potassium. It's going from a plus to a 0. So where is the electrons being gained or is it being lost? Well, we can see that the charge is being reduced. It's becoming more negative. So we can write that we are gaining an electron. So we are being reduced. So GER part. And then with oxygen, we have O2 minus and we have 2 of them in this case. It's going to become O2. So it's going to a 0 charge. So we can see that, oh, well, we're going to be losing, in this case, 4 electrons are going to be lost or oxidized. And that's the basic idea of looking at oxidation reduction, is how many electrons are being gained, how many are being lost, which is all we need to know for introductory chemistry for the fundamentals. There will be future videos on oxidation reduction. This is something that will come back and when we go over harder type of reactions later in future videos. So please don't forget about how all this works. And I hope this video helped you understand that electrons are transferred in reactions, especially when you're looking at single replacement reactions and combustion reactions. There are electrons being transferred. All right. Thank you so much for listening. And if it's your first time here, please hit that like and subscribe button and hit that and comment below what you thought. And thank you so much for being here, and I really appreciate it, and I hope you all have a wonderful day. Bye now.